microspheres or what have you, to really make this term very, very small. So in the end, of all these rates, what's the right hierarchy? What would you like if you were engineering a system? Well, ideally, you'd like this thermal decoherence rate, which you could also think of very practically as just the heating rate, the rate at which phonons are being thrown into your mechanical system, much less than kappa. I say much less than kappa because kappa is going to be the upper bound on your cooling rate. It's how fast energy can leave the system, because sideband cooling means all the energy has to go out in the photon field. So this inequality here says that I can cool to less than 1 quanta, provided that I'm in the resolved sideband regime. So I put an omega m all the way out here. The idea that you can make G even bigger than kappa, that means you can really use the full bandwidth of the cavity, and in fact you can really even get into the strong coupling regime, where I can imagine having full control over an excitation and moving around the effective Bloch sphere that is a cavity-like excitation and a mechanical-like excitation. So again, just to reiterate what I'm going to say with a little bit of cartoons, I picture some ideal mechanical mode of whatever frequency it has. It's of course always going to have some quality factor, some dissipation. The fluctuation dissipation theorem tells us that's precisely where it's going to inherit its environment. Whatever's giving its dissipation, the effective temperature of the bath, it's going to tell you the occupancy of this mode. And for all the things we're talking about, you can easily make this approximation. It's just KT over H bar omega. Now we're going to come in with a cavity mode of some other frequency. It's also coupled to, usually it's the same temperature bath, but again, here we're thinking about the bath at acoustic frequencies, at mechanical frequencies. Here we're thinking about it at electromagnetic frequencies. So the bath at 10 gigahertz or whatever it is in our system is effectively cold, effectively zero. And then you turn on some coupling, and as I said, this G naught, the intrinsic coupling, if I don't put any pump in the system, it's kind of weak. There's a little bit of exchange going on here, but it's small compared to the dissipation in the problem. Interestingly, it's actually in my circuit, it's a little bit bigger than the intrinsic line width, but there's no real, nothing special that does. You really have to overwhelm the parallel combinations. What we're going to do, as I've said over and over, we're going to pump it. We're going to pump it so we get this so-called beam splitter Hamiltonian bridge tuned here. This wimpy G naught gets parametrically enhanced, as I've just shown you. And now I start to think of something that looks like this. Now G is big. It can be big, completely overwhelm this rate. And I'm going to imagine a weak coupling regime, meaning this G is still small compared to kappa. This is the regime in which people traditionally think about sideband cooling in. I can effectively take this block diagram, and now from the perspective of the mechanical mode, what it sees is a heating rate of phonons coming in, that's this gamma thermal, the mechanical equilibrium environmental temperature, times the intrinsic mechanical line width. And now it sees a cooling rate that's effectively, once G gets an excitation into the cavity, it's immediately dumped out because kappa is very, very large. So anything that comes from the mechanics into the cavity never goes back. It's always immediately falls out here. You get some effective damping rate that we've seen over and over. And as I said, this cooperativity that I told you about before, 4G squared kappa over gamma m, is just, you can think of very practically, is how much I damp compared to the intrinsic mechanical line width. And that's why I say, if this is of order 1, then I can cool by a factor of 2. If this is equal to your heating rate, then I cool to 1 quanta. And ideally what we all love is for this to be much, much bigger than over here and get arbitrarily close to 0. Something, hopefully someday, close to the trapped ions where it's no longer the problem in the system. That's the weak coupling regime. Now what happens as I turn G up even more? Apparently I have one more equation. Just as I said, the final occupancy of the mechanical mode, you could get just from a detailed balance type of argument, heating rate and cooling rate, and it's essentially just balancing these two things. Now we're going to go into the strong coupling regime. Strong coupling defined by G becoming large compared to kappa. I've put that it's also less than omega m. Wow. Good. I was all excited. Should I go back? Yes.
It's a question about the drive. So you're working with like a cold drive,
Yes.
I'm still a bit confused about this. I know that this is useful, but what would it mean to work like with odd couple? Is it possible? What would it mean to do?
Absolutely. I think about this a lot because at gigahertz frequencies, it's not impossible to have a literally hot drive, to really have your cavity in a thermal state. And I can still put a huge coherent tone on that, but now in quantum optics language, I should think of that as a displaced thermal state instead of a coherent state. If that were the case, there's what breaks down is now this could be some finite number. And essentially what you will do with your sideband cooling is equilibrate to balance this occupancy. So if your cavity has on average, let's say, 2 quanta in it, because it's not quite cold enough, the sideband cooling, all it could ever do is get your mechanical system to 2 quanta.
So it's thermal states, and when you take n to 0 is coherent state.
That's exactly right. That's right. And so I've made the approximation here in lots of the papers, or it's very straightforward just to allow this to be some number, because you're already doing it in the formula for the mechanical mode anyway. In almost any paper, even if they don't make it, it's easy to put that back in. And if I wanted to think about literally what's happening, I have a huge coherent tone. Normally think about radiation pressure forces at mechanical frequency as a beating between my coherent drive and the vacuum noise. That's a mechanical frequency away in Fourier space. Now, if I don't have vacuum noise, but I have thermal noise, well, there's a larger white noise background that's beating with this large coherent tone. That gives me a larger force, and a force that looks much more classical, that it does just as well as putting in phonons as it does removing phonons. And it drives you, and you get some new equilibrium that comes out exactly what you think it should be to the temperature of the cavity level. Do you have a question?
Me?
Yes?
No, I'm just.
Or you were helping me.
I'm just directing to that.
Good. All right. So yes, if there were some finite occupancy to the cavity mode, there would be a correction term. And you would also get another similar correction term if you weren't very far in the good cavity limit. So that you had to consider not just the process that scatters phonons to higher energy, but the one that scatters to lower energy too. That's effectively another heating rate. For the hierarchy as I've shown it, that can be quite negligible. That can be much less. So now the strong coupling regime. Now I have some excitations coming into the system. I have some very fast G, which I should now think about swapping excitations here on a very fast time scale. So unlike before, where as soon as they hit the cavity, they immediately fell out, now they can cycle back. You can see from a cooling perspective, this is actually detrimental. If kappa were too small, if somehow I were just too good at making a high Q electromagnetic mode, I could run out of cooling power in the system. Because if kappa is not bigger than my heating rate, then this mode will just continue to swap these thermal excitations back and forth. And maybe there's some cool dynamics to it, but the point is this hybridized system would not be in its ground state. So what you would really, really like is to have the hierarchy as I've shown. This first part tells me that the hybridized system is going to be near its ground state. And as I said, if you want to know the final temperature of the mechanical or now the hybridized mode, it's just a detailed balance argument. I balance my heating rate to the cooling rate. Because kappa is the bottleneck in the system, it's not hard to get from here to here, it's only hard to get out to the cold environment. This limits the cooling rate, and so you get this ratio over kappa. This G small compared to omega m, that's something where maybe it would be cool if you could violate that. In practice, it means your rotating wave approximation really breaks down. If you think about it, your mechanical mode, let's say we're starting at 10 megahertz, I'm now going to normal mode split it further and further. If I start to split it by 10 megahertz, I'm pushing one of those hybrid components through or near zero. And that's where you might think about ultra-strong coupling effects. And again, this is of a driven system. Maybe there's interesting things there. Should note, it's not that crazy to think about. In my system, I mean, for these data, G was about 1/10 of omega m. For more recent things, it can be about 1/2. That's also what was about in Marcus Aspelmeyer's original strong coupling paper, was G kind of 50% of omega m. So these are effects that might be interesting from a theoretical perspective in realizing if there's useful things that go on there, not just craziness and breakdown of approximations. And the last thing, if you really can have G bigger than both of these rates, now you can think of what the Kippenberg group calls a quantum coherent regime, a quantum enabled regime, one where now if you had a basis where you could put an excitation in, you could think about coherently exchanging that excitation between layers. Questions? So to get everyone on the scale, we've heard about a lot of different experiments. These are the frequencies and the rates in the problem for my system. Our cavity frequency is around 10 gigahertz. The cavity line width is a factor of about 100,000 down, and a line width of about 100 kilohertz. The mechanical mode's at 10 megahertz. You can see it's in the resolved sideband regime by a fair fraction. The mechanical mode also has a Q of a few 100,000, so its line width is down here at about 30 hertz. G, I've showed you, is parametrically tunable. At the vacuum level, it's about 200 hertz, it's over here. But by putting a few million photons in the cavity, we can pump it up so that it becomes larger than kappa, gets up to about a megahertz. And now, like I said, what we care about if we want to talk about the temperature of the system is what is this thermal decoherence rate? Hopefully, if we're doing well, it's somewhere in this window. We know it has to be bigger than gamma m. If my fridge was just cold enough so it's in the ground state to start, this thermal decoherence rate is just your mechanical alignment. And the ratio that we have here between kappa and gamma m, it's close to 10,000. So as long as our mechanical oscillator doesn't have 10,000 quanta in it, we should be in business to reach this full control regime, the quantum-enabled regime. So now what we got to do is measure how cold the mechanical mode is. As I said in the very first talks, this is essentially going to be, yes?
Sorry, can I ask a question on the last slide?
Yes.
This is the gamma thermal scale is n-thermal, whereas G scale is rare number of photons in the cavity. So wouldn't you give that the gamma thermal is more than the coupling?
I haven't followed, so maybe just say it again. So gamma thermal doesn't really care about the number of photons in the cavity.
It's the number of photons, but the application of that.
Yes, so the way I would think about it, it's just my heating rate that's going in. And the effective temperature of my mechanical mode is always this heating rate divided by the damping. So it's getting colder. So as I turn up G, this capital gamma gets bigger and bigger, and this gets smaller and smaller. But what's in the numerator here, this rate is really the same. It's just some constant up here. Anything else? So all we're going to do here is noise thermometry. We're going to pump the system, pump it where we've always been pumping it, and look at the noise power in the sideband, just on a standard spectrum analyzer. That sounds very, very simple. We're going to look at the noise spectrum in power spectral density units of meters squared per hertz. If I integrate under that Lorentzian, if I integrate a power spectral density, that's by definition the mean square fluctuations, gives me x squared. And by equipartition, x squared is related to the temperature of the occupancy of the mechanical mode. The real problem with microwave systems, something we've fought with quite a bit, is even the best amplifiers, these moderately commercial ones that are made at Caltech, are quite noisy. They're about, at best, a factor of 10 from the quantum limit. In practice, with the components you put in there, feel like about a factor of 30. And then you're measuring a very, very small sideband on top of a large noise background. In principle, you could just average longer. There's nothing to prohibit you from doing that, from resolving it. In practice, it starts to get a little painful. By a little painful, I mean integration times can go from minutes to weeks. So the solution is pretty obvious. What are you going to do? We'll just get a better amplifier, throw it in there. In the cartoon form, it's pretty easy. You just draw a triangle and you point to where it should go. In practice, this is what was another parallel thrust of the Lanyard lab at Gilla, was really developing some of the first useful Josephson parametric amplifiers. And I'm going to describe that briefly here. What you can think about from a measurement standpoint, if you'd like to tune out and don't care about parametric amplifiers, it's a way to reach nearly shot noise limited microwave detection, to really realize measurement of the electromagnetic field, and in fact do exactly what you want, and that's measure exactly 1 quadrature of the electromagnetic field. What these parametric amplifiers are you make resonators. In this case, this device was like a Lambda/2 resonator. So I can really think of it in analogy with a fabric-Perot cavity. In the microwave, we don't have actual fabric-Perot cavities. We have coplanar waveguide transmission lines, like we heard about yesterday, with boundary conditions. And the 2 boundary conditions, we're going to put 2 capacitors. That's going to cause there to be a standing wave in this microwave transmission line, just like you would get in a fabric-Perot cavity. And now the magic is going to happen because on this center conductor, we're actually going to make it an array of squids. As we heard from Steve Gerber, Josephson junctions are the only nonlinear, non-dissipative circuit element. And that's not just useful for quantum information, that's precisely what we're going to use here, is their nonlinear nature. These little array of squids look at like an effective series of little inductors, and inductors that are nonlinear. If you pump them, they change their inductance. And nonlinear transmission line, that really realizes a Kerr medium. A Kerr medium where you can choose the size of the nonlinearity for whatever it wants to be. So you choose something that you can pump relatively strong, and if you pump a Kerr medium, you get these mixing elements in there. You can get gain out of the system. And that's in fact what we're going to do. What's nice about these is they operate at base temperature, at the same temperature as your device. So you don't need to have long, lossy elements that connect to your amplifier to the thing of interest. And the intrinsic noise of these things, for quantum optics reasons, are really right at the same quantum limits of measurement. So in fact, if you look, there was Nature Physics maybe 4 years ago where they really quantified what is the added noise of this amplifier. That's what's shown here in yellow is kind of the noise performance of the amplifier. This level here in blue is just the vacuum noise coming into the amplifier. Isn't it all the fault of the amplifier itself? The amplifier does add a little bit of noise that we can still see, but again, we should contrast it with what's the added noise of these cryogenic HEMT amplifiers, which is up here in white. So you get about a factor of 30 improvement in your signal noise. And what I also said is nice is you can use it to measure 1 and only 1 electromagnetic quadrature. And that means you're not measuring simultaneously canonically conjugate variables. So you don't, in principle, have to add any noise. In fact, if you were measuring both quadratures in the electromagnetic field, your amplifier would have to add a noise that's like this green line. And we were very excited to show that this amplifier could, in fact, add noise even less than that. So the point is, you might ask why you're not fully ideally on this line. That's something actually the Lanyard lab has progressed closer and closer to. The performance is becoming phenomenal. These are the same type of amplifiers that enable the things like the real-time feedback in the Sideband group, or even some of the nice quantum limited measurements that are coming out of Yale now. So this is an insanely useful tool, which I'm excited we're a little bit ahead of the curve in using them for optomechanics. So the experiment, I started off in the beginning with it looking insanely simple. You have some circuit, you apply a sine wave to measure what comes out. I showed you with a cartoon, it looks a little more complicated. You have to do this in a fridge. You have to worry about things like filtering and amplification. If you really, really want to look under the hood, you're looking at an experiment that looks like this. This is in the Lanyard lab at Gilla. The big tall cylinder here is essentially a thermos. It's inside that is the cryostat. That's where the cold temperatures are. These are all microwave modulation and demodulation equipment. The detailed circuit diagram I won't bore you with. If anyone's interested in the real details, it looks like this. We do things like filter our pump just to make sure that we're not limited by any phase noise of the pump intrinsically. You can send it down to interact with the Optomechanics. In fact, what we do is we have another generator to actuate the parametric amplifier. We split this to actually keep our coherent pump drive from overwhelming and saturating our parametric amplifier. And we're just going to demodulate in a coherent way. Like I said, if you're really interested, we can talk about this later. So just to show you what the data looks like, now I'm going to measure one of these noise spectra. at Fourier frequencies, the mechanical frequency, 10 megahertz away from some 7 gigahertz pump. The y-axis is in meters squared per hertz. I've really calibrated it. You can see without the parametric amplifier, your noise floor is up here. With the parametric amplifier, you can see there is a mechanical sideband. This sideband is also buried in this noise. Like I said, if I average longer, I can see it. It's not just that the white noise level is bigger. It's a fundamental fact about measuring noise. The noise is bigger. That means this, which took me about 5 minutes to get this level of averaging, just to look pretty, to get that same level of RMS fluctuations would take about a week. So it really changes the way these experiments are done. To know the temperature of the mode, now all we're going to do is measure the area under that curve. We're all set. That area is proportional to the occupancy of the mechanical mode. As I said, to calibrate the system, to get it into real units, to know how many femtometers of motion we have, what we can do is vary the temperature of the environment and rely on equipartition and really see if the area under that curve follows a linear dependence. As we heard from Keith Schwab, it wasn't uncommon for the nanowire experiments to really follow equipartition at high temperatures, but at some low temperature to hang up, to no longer cool. Again, just because my fridge thermometer says 15 millikelvin, that doesn't at all mean the vibrational mode of this drum head vibrating at 10 megahertz should necessarily be at that same temperature. For these devices, it really does follow the cryostat temperature. And I think that's a couple things. I think the drums cool better than the nanowires just because they have more boundary conditions, more surface area to interact. The other thing that I think is crucial and often overlooked, what helps is I'm measuring this by putting very little energy in the system. I'm probing the cavity with about 3 photons in the cavity. You're talking about attawatts of power. And so usually it's the measurement power, it's the thing that's going to drive your system out of equilibrium. I told you all the drawbacks about using microwaves. We have these very, very wimpy photons with 10 to the 4 times less energy. That means our radiation pressure forces are 10 to the 4 times smaller, and the signals we're trying to measure are 10 to the 4 less. The advantage we get, one of them, is the fact that when I put 3 photons in the cavity, that's attawatts of power. And so these measurements are naturally compatible with measuring at millikelvin temperatures. Whereas this is going to be a big problem as the optical systems push to lower and lower temperatures. I think it's fully tractable, it will just need to be fought. So as we cool at our base temperature about 15 millikelvin, you're now talking about 30 quanta in the mechanical mode. Again, there's a couple things you should compare this to. First, you can say it's bigger than 1, so we're not done. We have some more work to do. But 2, you can say, how does this compare to all those heating rates and cooling rates I showed you earlier? Well, this now means you have a heating rate. If you use the 30 hertz mechanical line width and an equilibrium occupancy of about 30 quanta, you're now talking about a kilohertz heating rate, about 1 phonon per second, per millisecond. But we can compare that to kappa, and kappa for these devices is about 100 kilohertz. So there should be plenty of room to cool, at least to the level of 1 quanta and hopefully well below. So these are what the data look like as we turn up our cooling power. What's shown in the different colors are the different noise spectra. Again, we're pumping somewhere way over here. We're looking at the upper sideband, which is as resonant with the cavity as we can do. As we increase our pump power, we go down these curves. And you can see there are a couple effects that are happening. First, you'll see the noise floor is going down. This isn't because I've waterfalled the plot to make it look pretty in print. This is because I'm doing a better and better measurement. I'm interrogating the system with more and more photons, and I'm acquiring more information about its displacement. So my displacement sensitivity, this white noise floor, is getting better and better. The second thing you can see is that the mechanical line width is getting wider and wider. I'm dequeuing the mechanics in exactly the way that's good for sideband cooling. And if all is right with the world, the area under these curves should be getting smaller. The fact that I plot this on a log scale should already tell you that that's going on. So to look at these 3 things one by one, in the last couple minutes that I have here, if we first just quantify and say, what is this white noise background doing? What is the sensitivity of our measurement? Well, the sensitivity, our displacement sensitivity, just continues to improve as we put more and more photons in the cavity, just like 1 over the number of photons. If we measure with more power, we get more information. Nothing really non-ideal is going on here. And in fact, at our highest power, we're doing displacement sensitivities of about 10 attometers per root hertz. Now, any absolute sensitivity you should be a little suspect on, because LIGO has a very different scale with their huge masses. And in fact, their sensitivities in absolute units can be much, much better than this. Something probably like 10 to the minus 38, even the minus 10 to the minus 38, 10 to the minus 39. But if you were to compare to the relevant size scale in the system, the 0-point motion, that's what really tells you if you're impinging on quantum limits, really pushing the bounds. And the 0-point motion here is femtometer scale, so this can be far below that. In fact, that's the absolute sensitivity. But as I said, as you're turning up and up your power, you're doing a couple of things. You're dequeuing your mechanics, you're making it a lower Q mode. That's what I'm going to show you here, are the different rates in the problem. What's plotted on top is just the cavity line length. If everything were in principle right, it shouldn't be changing at all. In practice, we can see a very slight power level dependence. Power dependence to kappa. It actually gets a little bit better at high power, but that's something we usually measure. G, as I showed you before, just goes up as the square root of the number of photons in the cavity. And then what's plotted in red is the capital gamma, the optical damping that you have. At low powers, you're just measuring the intrinsic line width of 30 hertz. And at about 50 quanta in the pump, you now start to overwhelm and cool by a factor of 2, and you damp and damp and damp. In fact, you're damping all the way up to essentially the cavity, and essentially into the strong coupling regime up here. So the fact that your mechanical line width is going from something with a mechanical Q of 300,000 to something with a Q of 10 to the 4 worse, you're talking about less than 100, means it changes how I think about my measurement. So now if I also plot this noise background, this imprecision, and instead of plotting it for you in absolute units, in meters squared per hertz, if I plot it in quanta units, in other words, I said, if I have some mechanical peak of, let's say, 1 quantum in it, what's the signal to noise above the background? What is this imprecision in units of the quanta? So at first, when I measure and measure stronger, my noise floor just goes down and down and down, and my imprecision quanta goes down and down and down. And you see at about here, this noise background would correspond to maybe 30 quanta. So if I'm looking for a cold peak on top of that, I might have to do a little more averaging. Now, as I start to damp the system, as I start to DQ it, which that crossover, as I said, is right around 100 quanta in my drive, I do this trade-off. For every bit I do better in imprecision by pushing down the white noise floor, I'm also making the mechanical oscillator wider and wider. So that means my signal to noise here, my imprecision quanta plateaus. Now what's nice about this plateau is a direct fundamental measure of the quantum efficiency of your measurement. In other words, for every photon that scatters off the mechanics, that's really scattered to a sideband, how many of them do I collect? If I really want to hit the Heisenberg limit, I better collect every single one with unity efficiency. That means it can't be lost in the cavity, it can't be lost in the cables, and it can't be lost in my detector. So we don't hit that exactly. The fact that this is of order 1 means we're doing a pretty good job. In fact, the true quantum limit would be about a quarter quanta, or about a factor of 8 of that. And that's one of the lowest noise measurements that is out there. And this is thanks very much to that Josephson parametric amplifier. Another way to say it is you shouldn't be impressed by displacement sensitivity or force sensitivity. What you should always think about, what's constrained by quantum mechanics is the product of the two. That's something that's limited to be of order h bar. And in these devices, we're within about a factor of 5 of that. So that says why we're able to measure these very small signals. I haven't yet told you how small are these signals. So for the final data, here's what they look like. You start with a moderate pump. Your mechanical mode has about 27 quanta in it. That's the area under this curve. You get lower, lower, and lower. You can get something that's less than 1. You can now see this nice high Q mechanical mode is fat and cold, but that's what we're going for. Now I spent the whole first half of this talk talking about the strong coupling regime and thinking about, well, what's going on the scale of the cavity? So if I think about this curve, the mechanics is now about 4 kilohertz wide. But what if I looked at the same noise spectrum and just zoomed out on the x-axis? Instead of looking over a 4 kilohertz span, let's look over a 400 kilohertz span. Now if you do that, you can see this sharp mechanical peak is riding on top of a broad Lorentzian. That broad Lorentzian is the cavity mode that it's interacting with. And in fact, as you turn up the pump strength stronger and stronger and stronger, you can really see the normal mode splitting, now from the perspective of mechanics. Before we were probing the cavity and seeing the cavity's response function hybridized into these normal modes. Now we're looking at the mechanical susceptibility and seeing that I can't point to that and say it's mechanics and that and say it's electromagnetic, both are really both. So this is the other side of the coin, the other realization of the strong coupling regime that must be there. And what's also very, very nice is these numbers for the occupancy of this mechanical mode for this hybridized system are all less than 1. This is a system that's spending the majority of its time in its ground state, one of the long-standing goals in the field. So these are what the data look like if you plot them as a function of dry photons. You cooled from about 40 quanta down to about a third of the quantum, cooling the center of mass mode of 10 to the 12, something like that, atoms to each ground state. Now, again, if I try to apply the classical question, the classical test to this, I have mixed answers on this one. On one hand, what I've succeeded in doing is creating the most boring state in the universe, the ground state where nothing's going on. So no whistles or bells go off. And in fact, for this measurement, where what we're doing is we're doing noise thermometry on the upper sideband, this sideband should just disappear as you get colder and colder and colder. And in fact, that's what it should do classically as well. Looking at just the upper sideband doesn't give you some of these truly quantum signatures. What this does do, we've worked very, very hard to calibrate this y-axis. So we really do know, we've realized the system at temperatures that are relevant for doing interesting quantum stuff. And that's what I would say these measurements are. They're an interesting starting point to do the more exciting quantum information things that we'd like to do. That's what I'm going to push into with the next lecture. I think I'm going to go ahead and stop there and take your questions.